I guess without further ado, today Kathy will be giving a brief introduction to optimal control and dynamical systems from more of an engineering perspective. And yeah, this should be exciting. So I guess I hopefully won't take up too much of their recording time. It's going to be a lot of video, so I guess enjoy.
Okay. So, hi everyone. Today I will do a sort of background introduction in optimal control and dynamical systems. For folks in engineering or whoever has already taken a course on control theory, today's material may already be, I guess, trivial, but I've never done this before, so please just bear with me. And also, at any time during the talk, feel free to just unmute yourself if you have any questions and just yell it out. Right, so what is control theory and why are we doing this in the machine learning reading group? Well, control theory is the study and practice of manipulating dynamical systems. And it's inseparable from data science because the sensor measurements we get from those dynamical systems are essentially just data. But the characteristics of this data is going to be different from a statistical learning setting. Although in today's talk, we'll focus more on some of the classical material in control theory and not so much about how to integrate your favorite machine learning model with a dynamical system. All right, so first, let's look at some examples of how controls are used. So this is a PID controller. It's a feedback controller typically used for temperature or pressure controls. So this temperature controller, what it does is it takes measurements from a temperature sensor and its output is connected to a control element such as a heater or a fan. So that's a very, very simple, very everyday example. And another maybe not so everyday example is Boeing's maneuvering characteristic augmentation system. So the MCAS is a flight control law. It is a software that monitors the angle of attack of the aircraft. And it tries to push down the nose of the aircraft down when the angle is too high. And in recent news, apparently Boeing has installed MCAS onto their 737 MAX aircrafts. But apparently the pilots were not well trained enough to work with it, and therefore it has tragically resulted in 2 of the recent major air crashes. So there are many ways to manipulate the behavior of a dynamical system. So first, we can break down all types of controls into either passive or active controls. Passive control does not require input energy into the system. It's cheap, it's simple, and is often reliable, but it may not always be sufficient. So for example, stop signs at traffic intersections is a form of passive control. It just stands there and tries to I guess control the cars coming into the intersection, but it doesn't actively put into energy into how to actually regulate the traffic. And in contrast, active control requires input energy, and it can be further categorized based on whether sensors are used in the system, whether sensors are used to inform the controller. So within active control, open loop control relies on a pre-programmed control sequence. So for example, traffic lights are pre-programmed to regulate traffic dynamically at different times of the day. And traditionally, sensors are not involved in this system. Whereas sensor-based control uses sensor measurements to inform the control law. And within this category, disturbance feed-forward control measures external disturbances to the system. And then it feeds this into an open loop control law. So an example could be preemptive road closure near a stadium before a concert happens. And the reason why it's feed-forward is because the road closure does not listen to the actual traffic it gets in a continuous manner, and it doesn't listen, and it also doesn't I guess tell the traffic regulators how to dynamically I guess change your road closures. So in contrast, closed loop control measures the system directly and then feeds the sensor measurements back into the system. And in fact, many modern traffic systems actually embed sensors at intersections to detect traffic density, which will then inform the traffic lights on how to behave. And closed loop feedback control will actually be the main focus of today's talk. So here's an outline for what we'll be covering today. We will follow closely to chapter 8 of Brunton and Kutz book. And I'll first give the big picture of what a closed loop feedback control look like, followed by a discussion of stability and eigenvalues of a linear dynamical system. And we'll also talk about controllability and reachability. And then finally, we'll touch upon optimal linear quadratic regulator for optimal full state control. So the section pointers are, you can refer to the section pointers to which part of the book I'm referring to. Okay, so this is an illustration of the general framework for closed loop feedback control. So here, if you can see my cursor, YT is a vector of sensor measurements that comes out of the system and it gets fed into the controller. And then the controller outputs this U vector, which is a vector of the actuation signals. And essentially this gets fed back into the system to modify the states. And I haven't put in the notation for the states, but essentially we'll use X for the vector of state values that we are trying to measure and regulate. And in addition, we may also have external disturbances that affects the system in different ways. So, okay, so here, I think I forward a slide. So here, WD is the disturbances to the state of the system, and WN is a vector of the measurement noise. And WR is some reference trajectory that the system may need to keep track of. So together, this gives us a dynamical system given by this differential equation. And from now on, I will mainly use the dot notation, so dot x, to denote the time derivative of x. And the differential equation on the right-hand side, we have a model f that depends on the current state x, the actuation u, and the state disturbances. And the sensor measurements y is given by some function g, and it depends on, again, the states, the actuation, and the measurement noise. The goal is to construct a control law u of some function k, depending on your measurements and your reference trajectory. And we want to design this control law such that some cost is minimized. And this cost is essentially just evaluating how much effort you need to put into the system to be able to control and I guess to achieve stability. Any questions so far? So a classic example is this inverted pendulum problem. So so the inverted pendulum is essentially is just you have some arm and then you want to stabilize it while having some mass at the top. And if we let go of the pendulum at this inverted position, its center of mass is very high and it will cause the pendulum to fall and oscillate. However, we can design an open loop control to keep it in the inverted position by simply pumping energy at the base with a sinusoidal motion. So imagine having like a cart at the bottom, and then you have like the pendulum here. If you just let go at this position, it's going to oscillate or like fall completely. But if you keep on, I guess, oscillating at the base, it will be able to keep your pendulum upright. It will be kept upright, but it will be very unstable. Right. So it's not a I guess it's not the optimal form of control that we should be aiming for, because not only we have to be constantly doing that, which is energy inefficient, it's also sensitive to external disturbances. So for example, as we are stabilizing it by pumping at the base, and imagine someone just comes in and kicks our pendulum, then our pre-programmed sinusoidal motion will not be able to correct that. And this is when closed loop feedback control comes in. And essentially what we want to do is we want to monitor the angle that the pendulum deviates from the vertical position. So we want to be able to monitor this angle. And we want to correct the system based on the measurements of this angle. So there you have a feedback. So you measure the angle, and then you feed it to the controller. Why does it keep doing that? And then you measure the angle, you give it to the controller, and then the controller will calculate how much it should move the cart to be able to put your pendulum into back to the vertical position, inverted position. So this form of control, this closed loop feedback control, will give us a more robust and less sensitive result in terms of stabilizing the system. So to summarize, the benefits of closed loop feedback control in comparison to using open loop is that it allows us to stabilize an unstable system, and it can compensate for external disturbances, and it can also correct for unmodeled dynamics. So let's talk about stability and eigenvalues. But before we do that, let's first talk about how to linearize a nonlinear dynamical system. So recall that I've only written my my ODE this way, but I haven't said anything about F and G, which means that the system can be an arbitrary nonlinear system, and this is going to be difficult to deal with. So for simplicity, let's first ignore the external disturbances. So from here, I've just nuked the disturbances terms. And then, so we are left with the simpler setup. And then now we can consider a fixed point, x bar and mu bar, where if you evaluate the function f at x bar and mu bar, it will be 0. And then we can use a Taylor expansion to obtain this linearization, where this A matrix and B matrix is just the Jacobian of f with respect to x and u respectively. And similarly, the linearization also gives, also turns y into this linear form, where c and d are just the Jacobian of g with respect to x and u, evaluated at the fixed point. So now this seems to be a bit less less complicated, and we'll be able to derive many things from it. So this is the linear system. And now suppose we don't use control. What happens if we don't use control? And for simplicity, we're also going to assume that we can measure the full state. So our measurement is just going to be all of the state values, the state variables. So u is 0, that means these two terms are gone, and y is just equal to x. Then our dynamical system just becomes x dot equals to ax, and this is a very simple initial value problem, and the solution xt is just given by this matrix exponential e to the at multiplied by the initial condition. So whatever shape A is, A should be an n by n matrix if we have n states. Then this matrix exponential should also be an n by n matrix. Okay, so that's just rewriting what we had before. And how do we compute this matrix exponential? We only know how to take the exponential of a scalar, but A here is a matrix, and the matrix exponential for a generic square matrix is defined by the infinite power series. So e to the power of at is just equal to the identity matrix plus at plus some constant times a squared t squared all the way to infinity, to the infinite power. And obviously we can't directly compute that. So fortunately, when A is diagonalizable, this matrix exponential can actually compute it by leveraging A's eigendecomposition. So we can write with eigen decomposition, we can write A as the product of Q lambda Q inverse, where Q is the matrix, the columns of Q is just A's eigenvectors, and lambda is a diagonal matrix with the corresponding eigenvalues. Then the matrix exponential e to the at can just be written as Q multiplied by the matrix exponential applied to the diagonal matrix multiplied by Q inverse. And this term in the middle here is actually easy to compute because it's just equal to the diagonal matrix formed by taking e to the lambda t for every eigenvalue, which are scalars, and you put them at the diagonal. So this is easy to compute. And when A is not diagonalizable, we can write the diagonal matrix lambda in Jordan form and then compute the matrix exponential with simple extensions. I'm not going to get into that. We're just going to assume that we're in the nice case. Right, so now if we write the states as x equals to qz for some vector q, for some vector z, essentially we can just obtain z by multiplying q inverse to x. Then we can actually transform the system into the coordinate system defined by the eigenvectors. So you can write the dynamical system in terms of the time derivative of z. And by definition, this is just equal to Q inverse x dot. And x dot is, we can write x dot in terms of our original ODE. So x dot equals to ax. And then x by definition, we can plug in qz here. And then Q inverse AQ is just equal to our matrix of eigenvalues. So, right, so what we have done here is essentially we have transformed our dynamical system such that the transform states are all decoupled. So, so our new dynamical system is z dot equals to lambda z, but lambda is a diagonal matrix, and therefore you can view this as decoupling all of the states. And then furthermore, if we write the solution of the ODE in terms of the eigen decomposition of A, then this actually, then it's very intuitive because what it's doing is that the state, the solution is formed by first projecting the initial conditions into the eigenvector, the eigenspace coordinates, and then we advance this projected initial conditions into time t by using this matrix exponential of the diagonal matrix. And then finally, we use the Q to project it back to the original coordinates. So the eigen decomposition is very important here. And in addition to letting us compute the matrix exponential easily, it also tells us a lot about the stability of the system. Is everything clear here? Questions?
Nam had a question?
Yes. Hello? Can you hear me?
Hi.
Okay. First of all, I'm kind of confused about the semantics of the Z. So it looks like it's some arbitrary transformation we're introducing. So there's no constraint onto what the Q looks like. So Q is not necessarily invertible.
I should have mentioned Q is just from the eigen decomposition of A.
Oh, that's right. Okay.
Yeah. So Q is the Q's columns are just the eigenvectors of A. So you take that matrix, and then you can take Q inverse multiplied by X, and then you can get your Z, and then you can write. I guess you can have like a new dynamical system, but in this system, all the states are independent. Is that a question?
I guess the interpretation here is that Z is in eigenvector coordinates.
Yes, exactly.
Yeah.
Other questions? Okay. Right. Okay. So we've written our solution xt in terms of the eigen decomposition of A, But in general, the matrix A, which we obtain this eigendecomposition from, can just be anything. So therefore, the eigenvalues in this lambda matrix may be complex numbers, which means that for every eigenvalue, we can write it in terms of some number A, some real number A plus I times B, where I is an imaginary number. Using Euler's formula for a single eigenvalue, we can write its exponential, so e to the lambda t, as this thing here. So essentially, it's just e to the at multiplied by cosine of bt plus the imaginary number times sine of bt. The cosine and the sine terms here don't really matter because they'll always be bounded. What could be problematic here is the term e to the at, because t will the time step or continuous time here will always be non-negative. So if a is positive, a is a real component. So if a is positive, then that means as we take t to infinity, our system will just blow up. So right, and what that means is the system will diverge in the direction of that eigenvector, and this is going to be the instability of the system. So therefore, if all the eigenvalues have a negative real part instead, then the system is stable and the states will actually be driven to zero as t goes to infinity. And on the other hand, if any one of the eigenvalues has a positive real part, then the system is unstable. And if we just pick a random initial condition, then it's very likely that it will have some component in this unstable direction, causing the system to diverge. And this is mainly why we need control. So if we have control, then it's possible, it may be possible to regulate the eigenvalues of the system such that it won't go crazy. So coming back to our inverted pendulum example, to get the, I guess, notation straight here, L is just the arm of the pendulum, the length of the arm of the pendulum, M is the mass that we place at the top, and theta is the angle between the pendulum and the vertical axis. And our control U is just some torque applied at the base of the pendulum, and G is the gravitational acceleration. From physics, we have, I don't know how this equation is derived, but apparently we have this second order ODE that describes the dynamics of the system. So theta double dot here is just the second time derivative of our angle theta. And it's a sinusoidal function of the theta itself plus the torque that we applied. So writing the system as a first order differential equation and gives us a two-state system. So our first state is the angle itself, and the second state is just the time derivative of theta. And if we just use this equation here, then x1, because it's theta, then it's just taking, well, it's so d theta is just theta dot, right? And then taking the time derivative of x2, so theta dot gives us this. And then because this is theta here, you just plug in x1 into it, and that's how we got this system. So if we take the Jacobian of x dot equals to f, which is just this thing, so we want to take the Jacobian of this thing with respect to x and u, then we get these matrices. So here we have, okay, I'll read it. How do I turn that off? No. Sorry. Sorry, Zoom had a pop-up, and now I'm lost. Right, we were here. And then, right, so how we got these matrices is just we are taking the partial derivative of f, so this is partial derivative of f1 with respect to x1, and this doesn't depend on x, so it gives us 0, and with respect to x2, it's just 1, and then you're taking the derivative of f2 with respect to x1 and x2, and similarly for df du. And if we linearize at the pendulum up fixed point, so x1 equals to pi and x2 equals to 0, because it's a fixed point, which means theta is not changing, so x2 is equal to 0. x2 is our the rate of change of theta, so x2 is 0. And measuring the angle of the pendulum arm from this downward vertical position, so the inverted position is 180 degrees, which gives us x1 equals to pi. So plugging these numbers into the A and B matrices, we get this. And we can do the similar thing for the pendulum down position, x1 and x2 both equal to 0, we get this. The eigenvalue of the A matrix at the inverted position is just plus or minus square root of G over L. And obviously one of them has a positive real part, and this means it's an unstable position. And it's also, it matches our intuition about an inverted pendulum. At the pendulum down position, however, the eigenvalues of the A matrix has no real part, which means if we take the exponential, it will always be 1, so it will not diverge, and therefore this is a stable system. The good news is that even if we have an unstable system, we may be able to use closed loop feedback control to stabilize it. And this leads to the notion of controllability. Any other questions before I go into controllability? So okay, so here's again our dynamical system. Let's now assume that we have, so formally we're going to assume that we have n states and q control knobs that we can turn. And A is this should be n by n, this is a typo. A should be an n by n matrix, and B is a n by q matrix. Right, so let's again assume that we can observe the entire state and there are no disturbances. So controllability is simply asking the question, when can we use feedback control to manipulate the system into what we want? And if we can control the system, how do we design the control law U equals to minus kx for some gain matrix k to drive the system to the desired behavior? So we also sort of simplified the control law to just a linear control. Before we wanted to model U as a function of like a function of x and the trajectory, but here we are just going to assume we're using linear control. So with feedback control, we can write the dynamical system as x dot equals to a minus bk times x. So just plugging in U into the system. And hopefully we can choose the gain matrix K such that we can place the eigenvalues wherever we want, the eigenvalues of this thing. So now this thing altogether will be our A matrix. And we want the eigenvalues to have no positive real components. So as it turns out, the controllability of a linear system in the form x dot equals to a minus bk times x is determined entirely by the column space of the controllability matrix C. So C here is basically just concatenate all powers of A times B all the way to n minus 1. And if you recognize this is the span of the columns of this matrix actually forms a Krylov subspace. And this determines which state vector directions in Rn may be manipulated. Right, so there are 3 conditions that are actually equivalent. First is controllability. So the system is controllable if the columns of C spans Rn. And which means that to determine the controllability, you can just check the column rank of C. and see if that equals to n. Controllability also implies that it's possible to choose the gain matrix K such that the eigenvalues of A minus BK can be wherever we want. And this is really nice because it allows us to essentially control how stable we want the system to be in all the directions. And the last condition that's equivalent is that is reachability of Rn, which means that it's possible to steer the system to any arbitrary state within finite time with some actuation signal u of t. And we will mainly focus on controllability and reachability in this talk. Cool. Right, so first let's look at some examples. Before we check the controllability matrix, do you think we can determine whether the system is controllable just by looking at it? And feel free to yell out the answer if you know.
I think no, because the only thing u affects is just the second coordinate, which, yeah.
Exactly. So that's correct. It's not a controllable system because first of all, your eigenvalues are all real and positive, and they're also completely decoupled. But you only have one actuation signal, which means you only get to turn one knob, and the only knob you can turn is, so the only state that you can control is x2, and therefore we will not be able to control in the direction when the eigen vector direction 1, 0, and therefore the system is not controllable. We can also just verify it with the controllability matrix, which, if you trust me, it's just this thing. And you see that the two columns are linearly dependent, and therefore it's not controllable. So with the same system, with the same A matrix, where the states are decoupled, if instead we can now turn both knobs, so instead of just one U, we have U1 and U2, then the system becomes controllable because the states can be independently manipulated by U1 and U2. Again, verifying the controllability matrix C, we see that it spans all of R2, and therefore indeed the system is controllable. The last example is a bit more interesting. So we're back to having just one control knob, but instead of having a completely decoupled system, we actually have X1 and X2 being dependent upon each other. So now do you think this system is controllable? Takers? Okay.
Yes.
Yes. Thank you. Right, so it may not be as obvious, but it is indeed controllable. Even though we only have a single actuation, we can actually control X1 through controlling X2 because the states are coupled. And in this case, the controllability matrix is this thing, and as we can see, it spans all of R2, and therefore controllability is satisfied. Right, so checking the rank of the controllability matrix is just one way to test. There's also something called the PBH test that allows you to check the controllability of the system. So PBH, the Popov-Belovich-Hoytas test, is it basically says that the system x dot equals to ax plus bu is controllable if and only if the column rank of this matrix is equal to n for all lambda in the complex plane. So this matrix, you just take A minus some number in the complex plane, and you concatenate it with B, and you want to test whether this spans Rn. But obviously, you don't want to check for all lambdas in the complex plane. So the trick here is to notice that the first part of the matrix, so the A minus lambda I part, will have full rank as long as lambda is not an eigenvalue of A. And when A does have full rank, and since A is n by n, then it will actually give full rank to the whole matrix, to the whole matrix here, without even needing anything from B. So that's really nice. And what this implies is that when you do perform the PBH test, you actually only need to check for the eigenvalues of A and see if the overall matrix has full rank. So that reduces the complexity by a whole lot. And if lambda is an eigenvalue of A, then the matrix A minus lambda I is going to be rank deficient. And the null space is the span of the eigenvector corresponding to lambda. And this is where control matrix B comes in. So to make up for this rank deficiency, the columns of B must have components in the eigenvector direction corresponding to the lambda eigenvalue. And this is really cool because it sort of relates back to the examples we just saw with the controllability matrix. Like it relates the eigenvalues of A to what needs to be put into this B matrix, and like how many knobs we can turn. And if A has n distinct eigenvalues, then B only needs to account for one direction per eigenvalue. And because for each eigenvalue, the null space of A minus lambda I has rank 1, and so if you just sum up all the n linearly independent eigenvectors and call it B, so that B has a component in directions that can potentially give you rank deficiency. So B sort of covers all of the eigenvectors. Then you only need a single actuation unit to control the system. So that's really cool. But alternatively, you can also just draw a random vector from Rn and use that for B. And the reason is that from randomized linear algebra, you can show that it's possible to show that with high probability, any random vector in Rn will have a component in all eigenvector directions. So this is actually really cool. That you can just draw a random vector and have that be your your control matrix. Right. So the rank test that we just talked about only gives you yes or no answers. But in fact, some states can be easier to control than others. And this is where the Gramian matrix comes in. So the controllability Gramian matrix is defined by this integral from 0 to time t. And essentially, you just take the control matrix B transpose, and you sandwich that between the matrix exponentials e to the at or e to the a tau. And this is again an n by n matrix, which is often, and this matrix is often evaluated in at infinite time by taking t to infinity. So I'm not going to go into too much about how this matrix is derived, but the significance is that if you take any state vector x and then you do an x transpose wx, then the larger this quantity is, the larger, the more controllable the state is. And the eigendecomposition of W also tells us about how much we can steer the system in the direction of the eigenvectors of W with only one unit of control input. So this is the Gramian. The Gramian, you also have, I guess, a parallel version for observability. So this is only for controllability. You also have one for observability, but I'm not going to talk about observability in this talk. I'll leave that for the next one because it's more related to full state estimation and the common filter. Right. So we've talked about, so previously I've said that the three conditions are equivalent, which are controllability, reachability, and arbitrary eigenvalue placement. So in this section, we're going to see the equivalence between controllability and reachability through the Cayley-Hamilton theorem. So reachability, to recap, what it says is just that it's if your system is controllable, then it's possible to steer the system to any arbitrary state x of t in Rn in finite time with some actuation signal u of t. So the Cayley-Hamilton theorem is something from linear algebra, it's very easily stated. It just says that every square matrix A can satisfy its own characteristic equation. So the characteristic equation or polynomial is just the determinant of A minus lambda I. And this is equal to lambda to the power of n plus A plus some constant multiplied by lambda to the n minus 1 all the way to the 0th term. And this is equal to 0. So if this is satisfied, then you can just equivalently plug in your matrix powers, your A's powers, and then this equation will also be satisfied. So this is the Cayley-Hamilton theorem. And why do we need this? So the Cayley-Hamilton theorem actually allows us to express the power, the nth power of A as a linear combination of the lower order powers. So this is essentially just rewriting this equation by moving all of the lower order terms to the right-hand side. So that gives us this. And not only we can express the nth power of A as a linear combination of the lower order powers, we can actually do this for all higher order powers that are greater than or equal to n. And it's actually very simple. Essentially, just imagine you want to you have A to the power of n plus 1, and then you can write that as A times A to the n. And then, which means that you're multiplying an A to every term here. So you're gonna have an A to the power of n here. And then you're gonna take all of these into this position, and that will give you another 0th order term. And all the other terms you can group together and have this constant modified. So is that clear? And right, so this is just writing it just saying that, like, well, what I just said, all the higher order powers of A can also be expressed as a linear combination of the possibly different coefficients multiplied by the lower order powers of A. Is that clear?
Can I ask to review the contrast between the definitions of reachability and controllability?
Right. So controllability is whether we can design a K matrix such that the system is stable. So such that the matrix. Let me see if I have it somewhere close. Nope. Okay,
yeah,
there.
I see.
So controllability is whether we can choose K such that the matrix here only has eigenvalues with negative real parts. And reachability is whether we can is being able to steer the system to any, so being able to drive your system to any point in Rn.
I see.
And these are all equivalent.
Thank you.
Is that okay?
Yeah.
So going back to Hamilton, right? So this is pretty cool. And what's even more fascinating about it is that the Cayley-Hamilton theorem allows us to express infinite power series that gives the matrix exponential as a finite sum. So recall that earlier I've defined the matrix exponential e to the at to be this infinite power series. So I plus at plus all the higher order powers. And with Cayley-Hamilton, essentially you can have all these lower power terms, but then once you reach a to the n multiplied by t to the n, am I having a typo here as well? This is another typo. So once I reach a to the power of n, then I can write that as all the as a linear combination of the lower order terms, and also for all the future terms. So that will give us that gives us this, and the only time variant components in this equation is the coefficients. So the coefficients are time variant, but this is now a finite sum instead of an infinite sum. So what does this have to do with reachability? Now we need to do a little bit.
Question.
Yes.
Sorry, those alphas, are they polynomials in T?
Yes, they are polynomials.
Finite polynomials in T.
Sorry?
They're finite polynomials in T.
Yeah, so essentially it's just, well, I guess this term will just be 1, and then so you're just grouping all the 1 over factorial terms with the t terms.
Okay, thank you.
Yeah.
They will
So
not be finite, right?
sorry?
They will not be finite, right? Because you have to take care of all the infinite powers of T.
No,
Right.
because all of the higher order terms can also be written in terms of the lower order terms. So
Of A, the powers of A, but not the powers of
no,
T.
the powers of the powers of T as well. Because if you have, so say you have some coefficient like T to the power of n plus 1, then wait. I think you may be right. I wonder if you can absorb that into these coefficients though. Not sure. Can't do it on the spot. But like being able to compute the powers of well, these coefficients is, I guess it's not the I'll need to verify this, but I don't think this is the main issue here. The point here is that we're going to use this and show the equivalence between controllability and reachability. I can do some doodling after this, and I can talk to you afterwards. Is that okay? Was that Boyan?
Fine, thank you.
Just for Kathy's benefit, Philip Lowen wrote that these are power series, which I guess answers the question.
Right. So right, so reachability. With control, so this is what I haven't shown you. I've only showed you the solution of the system without control. So with control, the solution of the system is actually given by this integral where you're integrating from 0 to t, and this is the matrix exponential. This is the matrix exponential multiplied by the B matrix as well as your actuation u. So so therefore, because this is essentially any state, then we can define reachability as if a state Xe is reachable, then it means that there exists some actuation such that this is satisfied for finite t. And right, so from here we can first write our matrix exponential using what we had from this page. So we can write it as a finite sum, finite power series. And then the next step is just chop up the integral into bits, and then taking this b, and then taking this power of a and b out in front. And then this is essentially just the inner product between this matrix and this matrix. And so essentially this is just what we saw earlier. This is the controllability matrix. And this is some matrix with linearly independent rows. And therefore, the only way for all of Rn to be reachable is when the columns of the controllability matrix to span Rn. Because if it doesn't span Rn, then it means that when we do the projection, then some states Xe will not be reachable. It will go into the null space. And if C has rank n, then we can also just design some actuation U to reach any state that we want. So if it's full rank, then we can always find some U such that we can map it to the state we want. So this is the quick derivation of the equivalence between controllability and reachability.
Does the measure of controllability defined by the Gramian, that W matrix that we talked about earlier, does that correspond at all to how small we can make T or expect T to be for the reachability definition?
Which part?
So yeah, you said that there was a measure with the Gramian of how controllable the system is.
Right, I see. So degree of controllability.
Yeah.
Degree of,
Does that have anything to do with how small you can expect T to be in the reachability definition?
I would, I'm pretty sure there is a connection. So if you're, so for example, if some state is,
Oh, I see.
I guess if some state is more controllable, then it's probably easier to reach that state. And I guess that would give you a sense of
I would say
the degree of reachability for that state, I guess. But I don't know a formal definition of degree of reachability. So, do you know anything
we're
about
assuming
it?
that we're yeah, I was gonna say, we are assuming that we're linearizing the like dynamics in some way. So like I assume that probably has something to do with how small of the differential you can actually use, if that's, I don't know if that actually is what you're talking about, because you can't necessarily take gigantic steps without like breaking that assumption.
Does that clear the question?
Yeah, I think so. Yeah.
I'm gonna, I still have some stuff to cover. I'm gonna to go faster. Right. So that's done. The reachability is done. Right. So the last topic that we're going to talk about, it's pretty short. It's about optimal full state control and the linear quadratic regulator. So coming back to our picture that we saw in the beginning, recall that if the system x dot equals to ax plus bu is controllable, then we have this other condition that says it's possible to arbitrarily manipulate the eigenvalues through a full state feedback control law, u equals to minus kx. So arbitrary eigenvalue placement. But if we choose u to make the system arbitrarily stable, then this can lead to some drawbacks. So we're going to spend a lot of energy. So this cost will be very high. We'll spend a lot of energy trying to control the system. And if it's overly stable, the system can also overreact to noise and disturbances. So therefore, it's not necessary that we always want an extremely stable system. And on the other hand, we want to try to seek a balance between, we want to seek the balance between stability and the aggressiveness of control. So optimal control is just choosing the best gain matrix K to stabilize the system with minimum effort, minimizing the cost J. So if we consider the cost function of this form, so J of t is just, so you have two main components. One is the cost of deviation of your current states measured by this cost matrix Q, and some cost of control. So you're trying to reduce this cost weighted by some matrix R. This Q matrix measuring the cost of deviation is going to be positive semi-definite, which means that we can always achieve zero deviation. But the matrix of R, the matrix R regulating the cost of control is always positive definite, because you always need to put in some effort. And these matrices are often diagonal, and they're tuned to weigh the relative importance of the states or control knobs. And yay, we have an optimization problem, and it's actually well formed, because you see that it's quadratics here. And right, I'm going to talk about the solution in the next slide. But this is where the linear quadratic regulator comes in. It's essentially a control law, u equals to minus k r sub r times x, and it is designed to minimize this cost function when you take the limit of t to infinity. It's linear because we're using a linear control law, and the quadratic just means the cost function is quadratic, and it regulates the state of the system to such that it will be driven to, the states will be driven to zero, and that's why the name is linear quadratic regulator. And since J, the cost J is quadratic, then there is actually an analytical solution given by KR equals to R inverse multiplied by B transpose X. These are actually conjugate transposes. I've turned all the conjugate transposes to just transposes. I don't want to complicate things. And right, where this X matrix here is the solution to an algebraic Riccati equation given by this thing. I'm also going to skip how this is derived. You can refer to 8.4 of the book and see a derivation. It's only 2 pages.
Kathy,
Yes.
would you mind reminding me the definition of R, please?
Right, so R is the matrix in the cost function that regulates how much control effort we want to put in.
So it's not explicitly defined, like it can just be something arbitrary there?
It's going to be user defined, I suppose.
Ah, okay, I see. Okay, thank you.
Right,
What's the
so,
little subscript R stand for on K?
sorry?
Oh, sorry, the little R subscript on K.
Oh, because just we want to differentiate this between the previous, well, the not optimal controls.
Okay.
Yeah.
Yep.
Sorry, nothing fancy here. Right, so essentially to obtain the optimal control, we want to solve this Riccati equation. And fortunately, there exists numerically robust implementations to solve this in like MATLAB and other numerical packages, but it's very expensive for high dimensional systems because it's cubic. Solving this is cubic in the number of states you have. And this motivates research in using reduced order models, which essentially tries to achieve the same goal with fewer states, dimensionality reduction. Right, I think that's all I'm going to cover today. So to summarize what we have covered, we talked about closed loop feedback control and saw the general framework. We discussed stability and how to determine it from the eigenvalues of a linear dynamical system. And we talked about controllability and reachability and their equivalences through the Haley-Hamilton theorem. And then we finally touched upon the linear quadratic regulator, which is the optimal full state control for a linear dynamical system. What we didn't cover is, I mentioned we didn't derive the Riccati equations for LQR, and I also skipped observability and full state estimation and the Kalman filter. So hopefully Ben will talk about this in the next talk. Right, so hope you enjoyed it, and I guess we'll gather next week. Oh, and also I highly recommend the book and the video series by the same author. They pair very nicely. If you're interested, you can check out both references. That's it.
Thank you.
Other questions? Final questions? No? Okay, I guess we can call it order.
Thank you very much. That was a great summary.